Okay, so we're going to move on from manometers to something that is useful. Buoyancy. Um, yeah, buoyancy. So, buoyancy is just estimating the buoyant force on a submerged object. And the buoyant force is the force trying to push an object out of a fluid, right? This is super useful for calculating whether or not a boat will sink, for example. Um, I don't know if you've heard, there's lots of talk now with COVID about people who have started settling in floating houses in the middle of like lakes and bays. This is also important for them too. Although mostly they don't calculate this, mostly they just put a bunch of stuff under their house and hope it floats. So let's be systematic about it though, because what separates engineers from other people is that we solve problems with numbers, physical problems with numbers. Okay, so we want to figure out what the buoyant force is on this this object here, this hollow rectangle with some weight m, and we want to know which model can we use to relate the weight and the pressures. So we need a model that relates forces to other forces. We know we're still in fluid statics, but what we're going to do is we're going to pick our model to be sum of our forces is equal to mass times acceleration, because it's a great model to start from. And we know fluid statics, so we know this is equal to 0. And anytime we bring out sum of the forces equal to mass times acceleration, we have to do a free body diagram because we have to figure out what all of our forces are. So let's do it. Let's figure out what all of our forces are. So we have a pressure force acting on all of the surfaces. Let's look at the bottom surface first. So we're going to draw our distributed force on the bottom surface. And this pressure is equal to, well, we know now, rho GH from our Pascal's law, also our law that delta P is equal to rho GH. Remember, for all of these, we have to assume that our fluid is static. And we have to assume that our density is equal to a constant. And finally, we're going to assume gauge pressure in all of this. Okay? So, this is equal to rho GH, that's our pressure, but that's not equal to our force. Our force would be to multiply that by an area. So we need to multiply it by A times B, where B is the width, depth into the page. Okay, so that gives us our force in that direction. Now we also have a force acting on the sides of our cube, or rectangle, and we know that the force here is equal to the force on the bottom of the rectangle, because at this point, at the corner, remember the first rule of hydrostatic tells us that the pressure is the same in all directions, right? So it doesn't matter if we're going up or sideways. At the corner, the pressure is the same. And we know that the pressure here, in gauge pressure, in absolute pressure this is not true, but in gauge pressure, the pressure is 0. So we know too that the pressure varies linearly with height. So we know that this is just going to be a triangle. We're going to draw the exact same thing over here, like this. Now, the last force that we have to add would be a weight. And this weight comes down like this, and it's just equal to m times g. Great, so let's add up all of our forces. Let's call this equation 1. So equation 1, we're going to tell the graders that we're going from equation 1 to equation 2. And then we're going to say some of the forces in the y direction. And let's Let's add a coordinate system to help our graders and help your future colleagues understand what you're doing. Y and X. Some of the forces in the Y direction is equal to, well, we have a negative mg, mass times gravity. Great. And we also have a rho g h a b, and that's in the positive direction, plus rho g h a times b. Great. So what have we learned? We know that this is all equal to 0. So we can set these two things equal to each other. 2 into 3, equation 3 here. We're going to say that m times g is equal to rho g. And now the important part here is HAB is this area here, this volume, sorry. So this is equal to HAB, which we're going to call the submerged volume of the object. So volume submerged. Call it V sub. Right? Great. And what we've learned is that this is the buoyant force. Oh, I never spell that right. Sorry. B-O-U-Y, buoyant force, and this is the weight of the object. So, as we would expect for anything that floats, the buoyant force is equal to the weight, right? More importantly, we now have a new model which just says F buoyant is equal to rho g times V submerged. And we use an upside down A for volume because later on we're going to use V for velocity an awful lot. And we want to make sure that we can distinguish between the two of them while we write it. So, great. So that seems really easy, right? Calculate the submerged part, done. Well, the hard part is finding out where the force acts on the body. Okay? And I'll just tell it to you now. The force acts, the buoyant force acts on the body through the centroid of the submerged volume. Awesome. So this is a great opportunity for you to practice engaged note-taking. How else would you rewrite that? Through the blank of the blank. Those are two words that you could completely redo in your own language, right? So through the centroid of the submerged volume, you could also write center of mass of V sub, right? And just doing that little bit helps you remember this and helps you understand it that much more, right? So I want you to keep doing that that kind of stuff. All right, so why is this important? Why is it important to know where the force acts on the body? And the answer is stability. And not the kind of stability you hope for in 5 years with a house, a job, health insurance. That's a different kind of stability. No, we're asking for stability that keeps boats pointing the right way. Okay? So what ends up happening is that the weight and the buoyant force form a couple. So for any object, let's say we have this, the weight, we would draw weights with red, right? The weight and the buoyant force will form a couple that will cause an object to rotate until those two forces are collinear, right? Because then they're stable and there's no more couple on the object. There's no more torque on the object. So knowing that, and knowing that the buoyant force acts through the centroid of the submerged volume, let's look at two objects that are submerged. And your gut is going to tell you right now which one of these is stable, right? Have you ever seen a stick floating upright in water? No, not unless you added a weight down at the bottom, right? But you've seen wide boxes float on the water all the time. Those are called boats, usually. So, but let's go through the work here. What I want you to try to do is to draw the center of mass, or the centroid, of the submerged section for both of these. And then also, assuming that the mass is distributed evenly in both, draw where the center of mass is for the entire object. Okay? So, I'll pause the video, try it out, give it a shot, spend some time on it. Struggling on a problem, by the way, is a good way to make sure that you are engaged in the learning. Too much struggle is a waste in time. And learning how much struggle is useful for you is part of learning how to learn, right? And it's one of the things that you go to college for. So struggle, but not too long. All right, I'll be here when you get back. Okay, well, I'm going to assume you're back. Okay, let's draw let's try to draw our centroid here. So our submerged volume goes from here to here. And I only know by heart the centroid for two objects. And those are a triangle and a rectangle. So the centroid for a rectangle is right in the middle of the rectangle. And the centroid for a triangle is 2/3 of the way down the rectangle in both directions. So I'm going to just estimate it right here. And so we add those two together. We're going to assume that the actual centroid is somewhere in between. So we can draw this going, oops. It's the wrong direction. We can draw our buoyant force going up from here. Okay? And our weight, our mg, is going to be in the middle of our object. Here going down. Mg, F buoyant. And now, which direction does our couple try to rotate our object? Go ahead and draw it. Draw it before I do. It's a race. Goes this way. So even though our boat is perturbed a little bit in this direction, the couple that results from the misalignment of the buoyant force and the mass of the object, mass of the boat, causes it to realign and start floating the way it was before. It is a stable equilibrium, if you will. Now this object over here on the right is a lot different, right? We're still going to break it down into some rectangles and a triangle. Now the triangle is so small it barely matters, right? So our buoyant force acts essentially at the center of this rectangle. I'm going to draw that up like that. And our mass acts at the center of our object, and it's going to go down. And that's going to produce a couple. Right? Now I want you to draw in the direction that that couple is going to rotate this object. Beat me to it. It's going to go this way. So we had a perturbation that rotated our object a little bit that way, and the buoyant force being misaligned from our weight is going to cause it to continue to rotate in that direction until it reaches a new equilibrium, and that new equilibrium is flat along the surface like that. Great. So if I asked you on an exam, or just because we were in an elevator and I was curious, which one of these produces a moment that is self-correcting, you would circle this one over here. Great. So the next two videos, I'm going to make two videos. One is going to be a quiz, not quiz. So again, do this with other people, spend a lot of time working on it. We will do this in class as well, for sure. I'm going to do breakout groups and have you guys talk about it. And then we'll do an example problem of a cube submerged with a spring attached to it, asking how far is the spring stretching to hold it in place. Okay? Great.